Welcome to the course on biostatistics and design of experiments. We will continue on this Weibull distribution, and as I said, the Weibull distribution is very important in reliability of parts, various biomaterials, implants, devices, machine parts, bolts and so on, actually even your tube lights, even your lights, your bulbs, your laptops. So, anything can have a reliability, and Weibull distribution can be used there actually. Okay. So, it determines the time to failure, how many days it may take to fail, or how many hours it may take to fail, how many weeks or years it may take to fail. So, it has got 3 parameters: shape parameter called beta, scale parameter called eta, threshold parameter called gamma. Okay. So, beta, eta greater than 0, gamma can be less than 0 also or greater than 0. Gamma is helping you to shift the entire equation to the right depending upon the gamma value. Beta is called the shape. Okay. So, as the beta goes up to 3, you end up having a normal distribution. Okay. If the beta is lower or higher, you can have a skewed distribution, left skewed, right skewed and so on. And eta is a scale parameter. Okay. It sort of tells you where the maximum occurs actually. So, lower eta, so the maximum occurs at lower value, higher eta, maximum occurs at higher value. And then there are other terms, they are called Weibull reliability matrix. Okay. So, 1 minus reliability can be unreliability. So, it is given by this formula, E minus T minus gamma by eta beta. So, if your gamma is 0, okay, that means if the threshold is 0, then you can call it RT is equal to U minus T by eta raised to the power beta. Okay. So, as you can see, depending upon the beta, you can have different types of curves here. Okay. You can have different types of curves depending upon the beta value here. Okay. Then we call the Weibull failure rate function, which is given by this beta by eta t minus gamma divided by eta beta minus 1. So, if I remove gamma, so it will become beta by eta t by eta beta minus 1. Okay. So, if beta is less than 1, beta is less than 1, the failure rate decreases with time. If beta is equal to 1, failure rate is constant with respect to time. If beta is greater than 1, failure rate increases with time. Okay. Then we introduced another term, that is called the mean time to failure, that is mean what is the average time for failure, is given by this relation gamma plus eta, and this is a gamma function of 1 by beta plus 1. Beta is your shape factor, gamma is your moving factor, okay. Eta is your scale factor, and this gamma function is given by, so please do not confuse with this gamma and this gamma, this is a gamma function and this is a gamma parameter. Okay. So, this gamma function is given by 0 to infinity e power minus x raised to the power n minus 1 dx. Okay. So, you do not get scared by this. So, depending upon the term inside, we will know what is the gamma function value using this table. So, for example, gamma 1 is 1, gamma 2 is 1, gamma 3 is 2, gamma 4 is 6 and so on actually. Okay. The median life or B50 life for the Weibull distribution is given by gamma plus eta ln 2 raised to the power 1 by beta. Okay. We are going to use these at some point. We did some problem in the previous case. We can use it especially in biomaterial body parts. How long, what is the probability that the biomaterial will last for so many hours. So, that sort of problems are attempted. Now, I need to know how to get these parameters, like how do I get beta, eta, gamma from the data, and that is what we are going to talk about in today's class. So, if you take the unreliability function and you get rid of this gamma, okay, you get rid of this gamma. So, 1 e power minus t by eta beta, and then okay, 1 minus, that gives you the unreliability function. This can be linearized last time I mentioned this can be linearized. Okay, if you keep linearizing this, okay, how do you linearize? You take the logarithm on both sides, okay, then again you take logarithm and so on. So you end up having ln of 1 divided by 1 minus qt is equal to beta ln t minus beta ln eta. Okay. So this looks like a linear regression relation. This is y, that is on the left hand side, t is your time, ln t is your x, so beta is your m slope, and this whole thing could be the intercept. Okay. So if I plot this whole thing as a function of ln t, I will get the slope as beta and the intercept as minus beta ln of eta, right. Okay. So it is very easy to do that, but it is not very easy to do that because we need to look at many things as we go along. Okay, there is something called median ranks which you need to calculate, and then you need to plot that actually. So we need to determine the appropriate y plotting positions, because I need to know how to do this. Okay, this is the y plotting position, so I need to know this, right. So in order to do that, it is a bit tricky. First we need to determine a value indicating the corresponding unreliability for that failure. Okay. And the general method that is used, it is called a median rank for each failure. So the median rank is the value that the true probability of failure qt should have at the jth failure out of a sample of n units at the 50% confidence interval. Okay. So how do you calculate median rank? We use this formula j minus 0.3 divided by n plus 0.4. j is the failure order and n is the sample order. So if I have 10 samples and this particular part fails at the third position, failure order is 3, then 3 minus 0.3 divided by 10 plus 0.4, that will be the median rank of that particular part. Understand? So the whole problem here is how do I estimate this q? In order to estimate the q, there is a approach called median rank for each failure. So we are trying to determine that, it can be calculated by using this particular formula. You think it is of no use, but then look at this problem. So a company has two designs for manufacturing hard diaphragm valves. They call it design A, they call it design B. The desired reliability at 400,000 cycles is 0.9, that is 90% of the valve should survive at least 400,000 cycles. So you take 10 samples from each of these design and they were tested, and at which cycle they failed is plotted here. So for example, this sample 1 failed at 726,044th cycle, sample 2 failed at 615,432nd cycle. They are all from the design 1 or design A. And if you look at these samples, the sample 11 which was taken from design B failed at 529,082nd cycle. Okay. Now the question is, how do I calculate this qt, okay, the unreliability? So what do we do is, first we need to organize this data. Okay. First take design A, let us do design A, put this data in Excel for example, and then sort them in ascending order. So 384.558, this sample fails the earliest, right, within a very short cycle. This will come first and then this will come second, like that, you put them in that order. So rank them 1, 2, 3, 4, 5, 6 up to 10. Okay, now the question is, how do I calculate this q? In order to calculate this q, as I said, we need to use this Bernard's approximation. Okay, j minus 0.3 divided by n plus 0.4, j is the failure order, okay, n is the number of data points. Here n is 10. Okay, so this particular has a failure order of 1. So same thing, I am putting it in Excel for example like this. So this has a failure order of 1. So 1 minus 0.3 is 0.7, 0.7 divided by 10, 0.4 will be 0.067. Like that, for each one of these items you find out a median rank. Okay. Then you calculate 1 divided by 1 minus median rank. Okay. Then you take logarithm of that, then again you take logarithm of that. Why do you need to do all this? Because if you remember, logarithm of 1 divided by 1 minus qt versus logarithm of t is what we are going to plot. So, in order to estimate qt, we use this type of approximation, the median rank approach, and the median ranks can be calculated using Bernard's approximation. Do you understand? So, we are doing logarithm of this, and then other side is to do the logarithm of design A cycles, that is logarithm of each one of this. Okay. So, you are going to plot this in the y axis, this in the x axis. So, when you plot these two, as you can see from our figure, slope will give you the beta and the intercept will give you minus beta ln n. So, if I divide this by this, I should be able to get my eta. Okay. So, I am plotting logarithm of 1 divided by 1 minus median rank, because median rank is considered to be your qt, then this is the design cycle, logarithm of design cycle, data falls here, you get the slope is your beta, okay, beta, and then the other parameter eta is calculated by ratio of intercept by slope, okay, because that is given by this beta. So, if you divide, okay, you will get the eta is given by this. So, beta is 4.25, that is the shape factor, eta is 693,380. Okay. So, what is the question? The desired reliability at 400,000 cycles is 0.9. Okay. Now, we can calculate the survival probability using the Weibull function available in Excel. We know 400,000 as our data x, and we know beta as the alpha as 4.25, beta as 693,380. Okay. When we do that, we can calculate, get the survival probability. Let me show how to do that. So, we have Weibull BULL 400,000 comma 4.25 comma 693,380 true. Okay. So, we get 0.092, that is the survival probability for 400,000 cycles, 0.092. Similarly, we can do it for different numbers also. Instead of 400,000, we can do it for 300,000, we can do it for 500,000, and so that gives you survival probability for different cycles. Okay. So, we get 0.028. Okay. And similarly, we can do it for 500,000 also. Okay, so that gives you a survival probability of 0.22055. So, for different values of these cycles, like 300,000, 400,000, 500,000, we can calculate the survival probability using this Weibull function. The other one, the design B, same type of calculation, and we can determine the survival probability. Okay. And then from these two we can decide which design to accept. This is how you need to do. It looks very complicated, but then it is a very useful type of approach. Let me explain once more for the convenience. Okay. So, we are looking at the reliability. The reliability function is given by this, okay, E minus t by eta raised to the power beta. Okay. So, the unreliability will be 1 minus that, 1 minus E minus t by eta raised to the power beta. Okay. Now, I want to estimate the etas and beta from the experimental data, and then use that eta and beta for performing some calculations. So, how do I do that? Now, if I take logarithm of this data, okay, this equation, this is the unreliability equation, qt is equal to 1 minus e, take one logarithm, then again I take logarithm, the equation ends up like this. So, this looks like y, this is your x, t is your time, slope will give you beta and intercept will give you this whole thing, right. So, we can calculate beta and eta that from the experimental data, okay. But it is not so simple, we will come across that later actually, but basically if I am able to get a q, that is if I am able to get an unreliability value, then if I plot keep that as my y axis and then ln t as my x, then from the slope and intercept I should be able to get beta and eta, okay, and then I can use it further for other type of calculations later. Now, how do I do this? That is where the median rank for each failure comes into picture. That means you need to calculate the median ranks for the failures. Okay. What do you do? Median rank is the value that the true probability of failure should have at the jth failure out of a sample of n units at the 50th percent confidence level. So, how do you calculate median ranks? It is given by this particular relationship called Bernard's approximation. Okay. This is equal to j minus 0.3 divided by n plus 0.4, j is the failure order, n is the sample size. So, if I have 20 samples and if a particular sample failure order is say 4, then j will be 4 and n will be 20, okay. Okay, that will give me my qt. Okay. It is not so simple as we come along later. A company wants to compare the dependability or reliability of two proposed designs of hard diaphragm valves. So, they want to have at least 90% of the valve should survive 400,000 cycles. So, they have two designs, they have 10 samples from design 1 and check the number of cycles it takes for it to fail. So, you can see the sample 7 fails at this particular cycle the lowest, and the sample 4 survives up to 807,000th cycle. The design B, you have sample 15 failing at the earliest and sample 16 lasting for sample 19 lasting for a much longer time, sorry, sample 20 is quickest and sample 19 lasting the longest. So, we use and calculate the median ranks. So, you put them, first of all you arrange them in the order of increasing. So, this sample fails at the earliest, this sample fails at the last. Then what you do? You put a j minus 0.3. So, for this sample j is 1, n is 10, for this sample j is 2, n is 10 and so on. So, we calculate the median rank. Okay. Then 1 divided by 1 minus median rank is what you do. That means 1 divided by 1 minus 0.06, that will give you this and so on actually. Okay. Like that you calculate. Then you take a logarithm of this and then again take a logarithm, 2 times you take the logarithm. Why? Because if you remember this, you have to take 2 times logarithm and then you plot keeping this as y axis and logarithm of t as your x axis, okay. That is the design cycles is your t, right. So, you take the logarithm, you plot this versus this, okay. You get a beautiful straight line logarithm of design cycles here. Here you plot the ln of 1 divided by 1 minus median rank. So, the slope will give you the beta, and intercept divided by slope will give you the eta, okay, because see, as you can see here, this is the intercept, this is the slope. So, divide this by that, we end up getting the eta, okay. So, beta is there, eta is there. So, I can use the Weibull distribution for any value of x. For an example, I want to see, I want to last it for 400,000 cycles. I substitute here and then I put true, and I can calculate the probability. So, it is very simple. So, you have done it for design A. Now, you go about doing it for design B. You repeat the whole process. So, you arrange them in the ascending order. So, this will come as 1, then this will come as 2, this will come as 3, and so on, and this will come as 10. Okay, once you arrange them, then you calculate the rank, medium ranks. So, this will remain the same. Okay. So, 1 divided by 1 minus median rank also will remain the same, this also will remain the same. Only thing is the ln of design cycles will have different sets of numbers. So, when you plot that as the x axis and this as the y axis, okay, so you may get a different slope, okay, you may get a different slope and an intercept. Correspondingly, the slope will give you the beta for the design B, and corresponding eta will get for design B. So, you will have a beta and eta for design A. Similarly, you will calculate the beta and eta for design B, and then we can do a Weibull for design B using this Weibull command available in Excel, and then we can compare the results with that we got for design A. So, it is very simple to do, but it is quite an involved problem. This is a very useful type of approach, especially if I am taking samples and then measuring their failure rates. Okay. If you already I know the eta and beta, it is very simple. I can use the Weibull function to get the probability of survival and so on, but this is more like you collect the samples from their failure rates, you estimate the beta and eta, that means it is a curve fitting and parameter estimation, and then use that for further calculation. So, that way this is a very useful approach. And as I said, Weibull distribution is important, especially in biomaterials type of research, okay, like I showed you this problem. Okay. 2 designs are available for a hard diaphragm valve, and you want to decide which design to take up. Okay. I have some body implant and I want to know what is the failure rate, how long it will survive, will it survive for years or months or days, if I have different designs. So, which design will last much longer. So, in that sort of situation, Weibull distribution is very useful, and Weibull distribution has 3 parameters, like I showed you, the beta, okay, 3 parameters like I showed you, the beta, the eta and the gamma. Beta is called the shape. Shape means okay, whether it is like a normal or whether it is skewed left or right. The scale is the eta, it basically moves the maximum to the right or to the left. Okay. So, the maximum can occur later or earlier. So, obviously, if I want to increase the reliability, I want to push it more to the right. Eta, the gamma is the threshold parameter location. If gamma is 0, that means your result data starts from the origin, whereas if gamma is greater than 0, that means data is starting after the it is getting shifted, the whole curve gets shifted to the right, whereas if gamma is less than 0, the whole curve gets shifted to the left. So, basically gamma is what it does, it shifts the curve either to the right or to the left completely actually. Okay. So, these are the 3 parameters available in the Weibull distribution. So, we can use Weibull distribution for determining reliability function like we discussed about recently, okay, and then we can use it for failure rate function, that means what is the rate of failure as a function of time, whereas in the reliability what is the reliability as a function of time, okay, after 1 year how reliable it is, after 2 years how reliable it is, after 10 years how reliable it is, like that. And then we can calculate the mean time to failure, what is the mean time for it to fail, and then here the equation looks like this. This is a gamma function, okay, which is given by this relationship. And then we can also calculate median life, okay, median life of this of a data set. Then we can also calculate unreliability function Qt, which is given by 1 minus the reliability function. 1 minus of this will give you the unreliability function. Okay. So, there are different functions available in Weibull which have their own usefulness and significance in many problems which involve reliability. And as I said, reliability is even important whether you take a light bulb, whether you take a laptop, whether you take switches, whether you take a heart valve, or whether you consider an implant, and so on actually. So, we will continue on some other topic in the next class. Thank you very much for your time.